with our material on continuity and differentiation. Where are we here now? So what we were covering last time, well, last time we did a proof of the chain rule. It was the main results we saw last week. Proof of the chain rule. And we worked also with some other properties of differentiation, inverse functions, parametric differentiation, and so on. And I left you to read through sections on implicit differentiation and logarithmic differentiation. And so what's left to do in the chapter is to look at some application areas for differentiation. And I've got 4 of them outlined here. Of course, in the rest of your mathematics study in 2nd and 3rd year, you'll see lots more applications of the concept of the derivative to a much deeper and fundamental level and much wider applications, especially when you come on to doing solutions of differential equations, both solving them numerically using computer algorithms to find approximate solutions, but also using certain analytic or exact methods for solving them, or various qualitative ways of getting information about answers or features of solutions to differential equations. So those topics feature very heavily in 3rd year courses like the ordinary differential equations and linear algebra course, the partial differential equations course, and the 2nd year course on it's called Introduction to Mathematical Modeling and Numerical Analysis. Those kind of things feature heavily. And in the mathematical methods core unit, which everybody takes in 2nd year. So, you know, lots more applications to come, but things that we're going to look at in this chapter are the finding and classifying of stationary points of functions, and kind of associated to that various rates of change problems or optimization problems. The topic of curve sketching, which kind of ties together a number of things. Given a certain function, being able to pull certain relevant features about that function out to produce kind of rough sketches of what the graph of the function might look like. And then some pretty simple problems in mechanics, looking at the motion of bodies under the influence of gravity, typically. Those are little applications of Newton's laws. So we look at the position, velocity, and acceleration of a particle. And those 3 concepts, the position of something, its velocity, and its acceleration, those are all linked by the concept of the derivative, because velocity is the derivative of position, the rate of change of position, and acceleration is the derivative of velocity. Acceleration is the rate of change of velocity. So, you know, understanding the derivative is key to solving problems in those areas. So that we'll start that tomorrow. I'll do the finding and classifying stationary points tomorrow. But for now, we just want to return again and just have another little look at the concept of power series or Taylor series for functions, okay? So it's just a short little section here, and we just want to look at a few things to do with these and maybe look at a few example problems. So just recall in general, the power series is the name we give to a function that's defined by an infinite series, okay? So power series refers to a function sorry, that's not coming through. A function defined by an infinite series. I.e. something of the form f of x, it's a function of x. An infinite series, sorry, I should say an infinite polynomial series. An infinite polynomial series in the variable of for the function. Taylor series is a power series. Well, that's one where the coefficients, these AIs, are given in terms of the derivative of the function. So you can see the definition here. Zoom in a bit. Top of page 48. So we have some function, and now the first version of the definition there is kind of the general form. And what's going on there is we're expanding the function f around some base point a. So a is some fixed base point, and x is representing the variation away from that base point a. So this construction f of a plus x, we're thinking of that as a function of x. So a is some fixed point. And then the Taylor series gives you an infinite polynomial series for that. Infinite polynomial series, so it's an infinite sum of powers xn, going from x0, which is a constant, just the constant 1, x squared, x cubed, and so on. But the coefficients are coming from the derivatives of the function evaluated at the base point a. And then there's this scaling factor of 1 over n factorial as well. Now we'll investigate that a little bit, and we'll do a little bit to justify why it might be that those are the forms of the coefficients there. In fact, I'll do that now in a moment. A special case of it is where we expand around the base point 0. So where a is 0, then the left-hand side kind of simplifies a bit to just f of x. So you're looking at variations away from 0, so you're just looking at the value f of x itself. And then the derivatives of f are all evaluated at the base point 0. So that's kind of the standard base point in a way. Yeah, okay. So what's going on? 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 Yes. So what I'll show you now is some kind of a justification for the Taylor series. Okay. I don't call it a proof because it's got quite a large assumption in it, but it's an argument towards the existence of Taylor series. So what we're gonna make some assumptions to get this argument started. So I'll suppose f is a function. Suppose f is a function that is infinitely differentiable, let's say. Something like the exponential function or a sine function or cosine function or logarithm function, some kind of function that's built up out of these. Now here's really the main assumption behind it. Suppose it has a power series. So f of x is the sum, I'll switch back to using n equals 0 to infinity, a to the n, x to the n. So we suppose that the function f can be written like that. Well, under that assumption, what we can do is we can prove now that these coefficients an here actually have to be the Taylor series coefficients that are given there. So we'll investigate the coefficients ai. If we just evaluate the function f at 0, well, that's supposed to be this infinite sum an times 0 to the power n. But of course, all those powers of 0 are 0, well, except the first one, which conventionally is taken to be 1. Okay? So, which is where you have 0 to the power 0. So this just gives you the value A0. So that's pretty good. We've determined the value of A0. This implies A0 is f of 0, which agrees with the Taylor series definition here, because that is also equal to the 0th derivative of f. Well, what's the 0th derivative of the function f? The 0th derivative is just the function f itself, the function f differentiated no times, divided by 0 factorial, because 0 factorial is conventionally taken to be the value 1. Okay, so in any power series for f, the coefficient A0 has to be the value of the function f at 0. Then what we do is we differentiate the power series. So when you differentiate the left-hand side, you have f prime of x. Probably easier if I use this representation here, so that we can write it as A0 plus A1x plus A2x squared, etc. I'll use that form rather than the summation form. Now, we're making some assumptions here as well. The fact that you can differentiate an infinite series term by term, that does require some justification. There's no problem with differentiating a finite sum term by term, but the argument that says that the derivative of an infinite sum is just the sum of the individual derivatives, that does require some extra justification, but we're just going to gloss over those technical details at the moment. If we take this polynomial over here and differentiate it, you see this is just A0 is just a constant, so it has a derivative 0. You got A1 times x, that just gives you A1. Then you got 2A2x, and then there will be 3A3x squared, and so on. Now, if we evaluate this at 0, so the first derivative of f evaluated at 0, well, you see there's an x here in everything, so they all go to 0 except the first one where there's no x. So that just gives you A1. So we've determined the value of A1. A1 has to be the first derivative of f evaluated at 0. That conclusion over here underneath the other one. A1 is f prime of f over 0. And that also agrees with the Taylor series coefficient over here as well, for n equals 1. You can keep repeating this process, okay? So we differentiate again the second derivative of f. Well, the derivative of the constant A1 is 0. The derivative of 2A2x is simply 2A2. And then we've got plus 2 times 3A3x. And then coming up here, there will be 3 by 4A4x squared, and so on. And again, you evaluate this at 0, and you get 2A2, which will imply that A2 is the second derivative of f divided by 2. But again, that agrees with the Taylor series form. It's the second derivative of f evaluated at 0 divided by 2 factorial. Okay. So each time we see agreement with the Taylor series polynomial, Taylor series coefficient. So an has to be the nth derivative of f evaluated at 0 divided by n factorial. So you can discover that this is valid for every value of n. And you can do a little induction proof if you want to set it up exactly. I'll just put a little note here. We require something called uniform convergence. So we'll encounter that concept, I think, in the second year maths methods course. Require uniform convergence to justify differentiating the infinite series term by term. And we know the process of differentiation is linear, so the derivative of a sum will be the sum of the derivatives, and that you can extend that to any finite sum just by iterating that result. But the extension to an infinite sum is an extra leap. It doesn't just follow because of the linearity property. You need something stronger, which is this concept of uniform convergence, and that does hold for these power series. So that's some kind of an argument to justify the Taylor series. The only kind of power series that a function could have, if as long as it's infinitely differentiable, is the Taylor series. So it's not as if the one function could have many different representations as a power series. The representation is essentially unique. Okay. Any questions about that, or oops, okay? Any questions about that argument? So there's a reminder there of some standard Taylor series for some functions. First one's called the binomial series coefficients in the first one for that function 1 plus x to some power. And then you got the exponential, the sine and cosine function, the logarithm function, tangent function. Okay, and there's some exercises there at the bottom, which I might do. Yeah, let's do one of them now. So we'll have a look at exercise 4.1. And this is just really just to check that you're familiar with the concept of the Taylor series and how it links to differentiation, and just being able to do certain verification. So here we're going to task ourselves with finding the Maclaurin series expansion of this function, which is e to the x times sine of x in terms of derivatives. Well, let's just find the beginning of the series, okay? So we'll identify the first few terms. So our function is f of x, which is e to the x sine of x. So the constant term is going to depend on the value of this function evaluated at 0. Of course, when you evaluate it at 0, well, e to the 0 is 1, but the sine of 0 is 0. So overall, you get 0. So there is no constant term in the power series. So it must begin with at least an x. Well, but in order to identify that, we should differentiate it, f prime of x. But now to differentiate this, you see it's a product of two functions. It's e to the x times sine of x. So we'll need to use the product rule for differentiation. So this would be e to the x times cosine of x plus e to the x sine of x. Okay, using the product rule. So first of all, I've held e to the x the same. I've differentiated the second factor, and then I hold the second factor the same and differentiate the first factor. But of course, the derivative of e to the x is e to the x, so that's why it appears like this. And when I evaluate that at 0, well, again, I get nothing from this second term here, but from the first term, we're going to get e to the 0 times cosine of 0. So that will give us a 1 in total. So we could ask for the second derivative. Now, we could notice that this e to the x sine of x is, of course, f of x again. If we notice that, that will help us do the second derivative quicker because we already know what the derivative of f is. So again, we need to use the product rule on this first part. So it's going to be minus e to the x sine of x plus e to the x cosine of x. Is that right? Hold on a second, differentiate that. Well, that's saying differentiate that. And then it's going to be plus the derivative of f. Okay, because this was f of x here. So when you differentiate it, you're going to get the derivative of f. So we have to evaluate that at 0. Evaluate that at 0. Did we get anything? Well, f prime of 0 is 1. E to the x e to the x sine of x gives you 0. E to the x cosine of x will give you another 1. So it seems to be 2, I think. In fact, we could notice, it will make it simpler, that this is e to the x cosine of x minus f of x plus f prime of x. So let's just go and get the third term. We'll end it there. The third derivative of x, well, I'm differentiating this e to the x cosine of x. I've already done that. It's minus e to the x sine of x plus e to the x cosine of x. And then I'm differentiating f. So this is minus f prime of x. I'm differentiating f prime, so it's plus f double prime of x. And this evaluated at 0. Well, from these two, I get a 1. F prime of x gives me a 1. So it's a 1 minus 1. And the f double prime of x evaluated at 0 should give me a 2. So overall, I should get a 2. Oops, sorry, can't see that. Now, if I've done that right, if I haven't made any mistakes, so I'll hedge my bets against the fact I've made some mistakes there. We'll check it in a moment. So the series should begin. So we'll follow the Taylor series formula, or the Maclaurin series formula there, which is that second equation there. So the constant term is 0, so there's a 0. F prime of 0 is 1, so that will give me an x. F double prime of 0 is 2, so I should have 2 over 2 factorial times x squared. And the third derivative at 0 is again a 2, and that's over 3 factorial times x cubed. So that should be the beginning of the series. So that's, what's that? That's x plus x squared plus 2/6 or 1/3 x cubed. And it continues from there. I hope that's right. Anyhow, we can check that in a couple of ways. I'll check it using the computer in a moment. But we could also check it, as is suggested in the second part of the question, by using the power series, by using the given Maclaurin series for the exponential and sine. F of x should be e to the x times sine of x. Now, the series for e to the x begins 1 plus x squared over 2 plus x cubed over 6, etc. And this is multiplied by the series for sine of x, which is x minus 1/6 x cubed plus 1 over 5 factorial, whatever that is, 120 or something. 1 over 5 factorial x to the power 5, and so on. So f should be the product of those two series. And we know the power series are unique, so when I multiply all these terms by each other, I'll get another power series. I'll get another infinite polynomial series in x. But the argument we gave a while ago by differentiating the power series showed that the power series are unique. So I should recover this same series here when I multiply these. Now I've got everything of order x, x squared, and x cubed. So let's see, well, yeah, so when I multiply everything in here by the 1, I'm going to get an x and a minus 1/6 x cubed plus some other stuff, which will be x to the power 5 or higher. So I won't bother including that. When I multiply everything in here by the x, I'm going to get x squared minus 1/6 x to the power 4 and stuff of higher order. When I multiply everything in the second series by the x squared over 2, I'm going to get x cubed over 2 minus 1/12 x to the power 5 plus higher order stuff. Okay? So I'm multiplying the whole series for sine of x by each of the terms from e to the x. In turn, I'm just recording the ones that have any chance of influencing order x squared, or order x cubed. So let's see what I get here. Well, I do get an x on its own, so that's good. There's only that x squared, so I do get the x squared. That's good. X cubed is coming from a few places. A half x cubed minus a sixth. So it's a half minus a sixth is 3/6 minus 1/6, 2/6 is a third. Half minus a sixth is a third. So it is indeed a third x cubed. And that's the only way from multiplying these two series, it's the only way you can get x's, x squareds, and x cubes. All the other product terms are of order higher than x cubed. So they're not going to influence the beginning of the series. So that confirms I was correct here, that my series x squared, 1/3 x cubed up there, is the same thing as I get down there. Okay. So that's doing it two ways, working with the original definition of a Maclaurin series, and then also confirming the answer by multiplying their two series. Okay, there's another exercise there, question 3 down there, you could have a go at. And there's also further exercises in the end of chapter exercises concerning power series. So they crop up in a few different places. There's another one there, question 13 and 14, 15, 16, 17. Okay, so there's lots more questions there to get to grips with power series for. So 13, 14, 16, 17. Just like to finish today by showing you another way to verify it, which is using the computer, of course. And the computer can allow you to visualize the power series as well. So I'd just like to show you a little program written in Sage that, well, will be another verification of this work I've done here for this series. And I'll put a link to this little code cell. We're going to see a graph here as well. And I'll put a link to this underneath the lecture recording as well. So you'll be able to go in and experiment around with this as well. So we'll begin. That command var x just kind of sets up x as a symbolic variable. And once I have that, then I can define my function. So the function is the exponential of x. So we use x times sine of x. So when you go in and experiment around with this, you'll be able to substitute other functions in there and see the effect of putting other functions in there. I'll define a couple of functions. I'll define a function called maccof. This is going to depend on n. So this will just define what the Maclaurin series coefficient is. And the Maclaurin series coefficient is the derivative of f differentiated n times. So that command diff fn should differentiate fn times. Then you evaluate it at 0. And then we're dividing by factorial n. That's just a little one-line function that should return the Maclaurin series coefficient. And then I'll define another function, which will be Maclaurin series n. And we'll get this to return the Maclaurin series up to order n. So this should return sum of a certain list, and the list will be maccof I times x to the power I, and it should do that for I in the range. Now, range is a funny command. It goes up to, but not including the last argument. So when I do range n plus 1, that produces the range of integers from 0 to n. The funny range command. So I think that's looking right. So if I do Mac series 3, might get some error messages here. No error messages. That's amazing. That almost never happens, that you write some code and it works straight away. There's almost always errors to fix. You can see that confirms the work we've done over here. So I did Mac series 3. So that calls these various functions, and it should return the Maclaurin series for this function f at the top of order 3. And indeed, you got x squared, and the third x cubed. So that's great. You can have a look at it for order 10. Actually, if you do show, if you do in Sage, if you do the command show instead, it'll typeset it nicely. Using some nice things. It's got it going backwards for some reason, but appreciate it there. Now, I'll also get it. Of course, you can also now start putting in other functions as well. So you could have the exponential of x squared. It'll probably look even crazier. Oh, that looks okay. That's nice. So you can experiment around with this code, and you can use it to help you with the other questions as well, to verify your answers with the other questions. You can put in any function up there at all. What we'll also investigate, so we'll go back to order 3. We'll also investigate what the graphs of these things look like. So I'll set P to be a plot of the graph of f of x. And you do x in a certain range, say 0 to 10. Let's have a look at what that graph looks like. Okay, so there's the graph of the function x times sine of x from 0 to 10. Now it's going off to huge values here, because by the time you get to e to the 10, that's a huge number. You're multiplying it by the sine, so it's going to produce huge oscillations. Because the sine part will vary between -1 and 1, but the exponential part is getting huge really, really quickly. So the oscillations get really, really big. But I can add to that plot. I can add the plot of the Mach series. I'll do that across the same range, x from 0 to 10, give it a different color. And then have a look at the plot P. So you can see some interesting features here. You can see that the two functions, maybe I should pull the range back a bit, pull it back to 5. You can see that there's pretty good agreement between the two functions at the start, close to the base point, x equals 0. So up to about 1.5, the two functions, or at least at this zoom level, the red and the blue line, we can't differentiate between them, but after a while they start to diverge. Okay. But of course, we haven't taken the full Maclaurin series there. We've only taken the first 3 non-zero terms. With power series, the idea is, so a truncated power series, or some finite initial part of the power series, just gives an approximation to the function. And that approximation generally will get worse and worse the further you get from the base point. But if we add in more terms, which we can do, so let's go up to 10 terms in the Maclaurin series. I think those 3 10s there. Well, let's make it easier to change. I'll just create a variable capital N, 10, and we'll do the Mach series up to 10, and the plot of it up to 10 as well. So you see this, so the Maclaurin series that went up to x cubed only remained accurate at this zoom level anyway, up to about 1.5. But when you add in a bunch of other terms going up to order x to the power 10, you see you get much better agreement over a larger range. But then the two do start to diverge a bit. Okay, as you come down here, you see their values are starting to diverge. And they'll diverge quite a lot because this one, the Maclaurin series, will keep going down, but the exponential series will start to turn up again, like up to 20. It mightn't produce much of a graph at all because the divergence will be a lot, but yeah, so you can see what's going on there. So the red is the, what was it now? Yeah, the red is the approximation. And the blue is the actual function. Of course, the vertical scale is getting huge here, 100 million, 200 million, 300 million, and so on. So maybe dial that back a bit to sensible values. Okay, but it shows you how we can use some relatively, okay, I won't say they're simple. I used a couple of functions in there, but we can use the computer to check our working and also get a nice visualization of these as well. Okay, I'll leave it at 5. I'll put a link to this underneath the lecture recording, so you'll be able to go in, just click on the link and you'll come to a page like this and you'll be able to mess around with the code here. In particular, you can vary the number of terms in the series, vary the range across which you're plotting it. And if you just put a different function up here, e to the x squared times sine times 3x, you know, the code should work for that different function. You should see it's the beginning of its Maclaurin series and a graph of the function. No, that one's not too easy to perceive much in that one, but okay, it's there for you to use. And so for the tutorials, be working on those questions. Started at about number 13, I think. Those questions on power series in the exercises as well. Okay, we'll finish there for today.